Okay, everyone, welcome back. Thanks for joining us for the next section. In the previous section, we looked at how wind can cause ocean circulation, and we were mostly focused on looking at the sea surface. And so in this section, we're going to look at more circulation. So I want to start out by looking at this map of sea surface density. So this is, again, we're just looking at the surface here. And if you notice up here in the top left-hand corner, we're looking at the color bar that tells us what the colors on this map mean. So lighter colors mean lower density. This 1002 is very close to the freshwater density. And then if we look up here, the darker colors are higher density. So this is similar to some of the maps we've already looked at. So what I'd like you to do is pause the video for a couple seconds, minute, 2 minutes, 3 minutes, however long you need. And I want you to spend some time looking at this map and thinking about what patterns you notice, what stands out to you. What do you look at and think, wow, that's really interesting? What do you look at and think, I wonder why that looks like that? Is there a region of really high density that stands out to you? Is there a region of really low density that stands out to you? So I'd like you to pause the video for as long as you need and spend some time writing that down. And then once you're done with that, you can resume the video and we'll keep talking about what we see here. Okay, hopefully you took some time to look at the video and think at the map and think about what you were noticing. So I just want to spend a couple minutes highlighting some of the things that stand out to me that we're going to want to think about later on. And any of these that you have are great. I'm sure you have more than I'm going to talk about right now, and those are also great. There's a lot going on in this map, and we don't have time to talk about all of it, but certainly a lot of the things we're going to talk about apply in lots of regions. So one of the things I want to point out is that we have this region of really high density up here in the North Atlantic. That's the darkest color on the map, and it's very clearly focused in this North Atlantic region, maybe on up here into the Arctic a little bit. But one of the things that I think is interesting is if you look east or west along the same latitude, you don't see a similar region of really high density anywhere else in the north. Over here, north of Canada, we actually see a really light region. Same thing here, north of Russia, very light. And then if you look at the North Pacific, there's nowhere in the North Pacific that has that kind of high density. So that's really interesting. And we're going to want to think about that later. The other regions of really high density that we see are here in the Mediterranean, over here in the Red Sea and the Persian Gulf, and over here in the Caspian Sea. So that's another thing that's interesting, is those are other regions that are really high density. And then down here in the Southern Ocean around Antarctica. And you'll notice that in this projection, Antarctic looks ginormous. Antarctica is not really that big. It's just that when we spread the globe flat like this, it makes the southern and northern ends look very large relative to their actual size. So those are the regions of high density. You'll notice that along the equator is a little lower density, which is interesting. And then we see these little hot spots of low density next to some of the coastal areas. So that's something that we're going to want to think about. So those are some of the patterns that I see. As I said, I'm sure you saw other stuff. So I want to take the same approach, and we're going to first look at our sea surface temperature map again, and then look at something else and try to think about why do we see these patterns in density. So we've looked at where the density is different, higher and lower, but we haven't talked about why that might be. So I want you to hold that in your mind and think about what factors do I think are contributing to this. So we've looked at a similar map. This is a slightly different version. These are all maps that are from NASA based on their satellite data. So again, we have the color bar up here in the top left-hand corner. Dark blue is the really, really cold areas, and red is really warm areas. If it surprises you that the water can get down to -2 degrees Celsius, which seems like it should be lower than the freezing temperature. I just want to think about what about seawater might be a little different. So again, I want you to pause the video. I know you've already thought about this a bunch of times, but just think about patterns you're seeing, and then also think about like how these patterns you're seeing in sea surface temperature might be related to some of those patterns we saw in density on the previous map. So again, pause the video for as long as you need to write down the patterns. If you've already spent time on that, maybe you don't need as much time. And I'm just going to stop talking while you pause. Okay, so similarly to the density map, we can pick out some patterns. We can say, okay, well, up here in the northern and southern reaches, we have really cold temperatures, and those appear to be the coldest regions. Typically towards the equator, it tends to be a little warmer, although again, you'll notice that it's not uniform across latitude. Like off the coast of South America in particular, you'll notice that it's not as warm as it might be a little bit further west. You'll notice up here by the coast of Washington, Oregon, and Idaho, there's this colder protrusion down here. But typically it's warmer near the equator and colder towards the poles. And that's something we've talked about before. So I would encourage you to think about how you think these temperatures might be related to that density that we saw earlier. But one of the things I want to highlight in particular is if you'll notice up here in the North Atlantic, we talked in the previous slide about how this is a region of really high density, and that high density is not seen also in the North Pacific. But you'll notice that the North Atlantic doesn't appear to be a lot colder than the North Pacific. So if temperature is contributing to that high density, it's not the only thing that's contributing. And so typically when we think about temperature, warmer temperatures tend to correlate with lower densities, and that's because as the water heats up, it expands thermally due to the motion of the molecules, and so you'll have the same amount of mass, but in a larger volume. But we can see on this map, if we were to go back to the previous slide, again, where we see this region of really high density here, where we would expect, if we're just thinking about temperature, we'd expect that to be where the coldest temperatures are, or here in the Mediterranean, we have this really high density. And so if we go back here, we can see that the temperature isn't enough to explain that, because in fact in the Mediterranean it's pretty warm, and in the North Atlantic it's not warm, but it's not the coldest place that we're seeing. So that means that there's something else going on here. So as we all know, if you've spent any time at the beach and gotten a face full of seawater, the ocean is in fact quite salty. And again, so let's talk about the color bar up here in the top left. We're looking at what are called practical salinity units. And so these are technically a unitless unit, which is a little weird, but another way to think about it is this is the number of grams of salty things, which is not just like sodium chloride, it's a lot of salt factors. Anyways, it's the grams of salt per kilogram of seawater. So the dark areas are areas where it's really fresh, and then these light areas are where it's really salty. So again, I want you to spend as much time as you need looking at the patterns in sea surface salinity, seeing if you're seeing anything here that might help you explain some of the things we saw on the previous slides, or just patterns that make you think about how this might be related to what we saw on the previous slides. Okay, hopefully you got some time to think about that. I will say that this color bar always throws me off a little bit, and I sometimes am thinking about it backwards, but one of the things I want to highlight is let's look at where we're seeing really low salinity. So One of the places I see really low salinity is right here down in South America, and that, in fact, turns out to be where the Amazon River is outflowing. If we think about that, okay, well, that makes sense. There's a river, huge river there. So we might be able to take that pattern and apply it to some other coastal regions. So if we actually look up here where the Mississippi comes out, if we look over here where some of where the Congo River comes out, up here, this is the Bay of Bengal. There's a bunch of rivers coming out of India that all outflow into this basin. So you can see, okay, so places where we're having large rivers exit into the ocean typically seem to have really low salinities. And if you think back to our density map, you'll remember that we saw some of these highlighted regions where it was really low density. And so those often seem to correlate with where we're having those rivers. Okay, so that's one thing I want to highlight. Another thing is we can start looking at, okay, so where are the really high salinity regions? Like where is it very salty? And so one of the places we see is this Mediterranean region. We see the Red Sea and the Persian Gulf. And if you'll remember, those were some of those regions where we had really, really high densities. And so that's a contributing factor. And then the last thing I want to talk about is we've talked about this thing where the North Atlantic is very, very dense, but the North Pacific is not. And that we couldn't explain that just with the temperature and the way temperature influences density. So if you just take a look here and we compare the North Atlantic to the North Pacific, you'll notice that the North Atlantic is in fact quite a bit saltier than the North Pacific. So they seem to have roughly comparable temperatures, but the North Atlantic is a lot saltier. So putting that all together, we know that temperature influences density such that the warmer the water is, the less dense it is. But we also now know that the saltier the water is, the denser it gets. And that's because you're packing more molecules in between the water molecules. And so you get more mass per unit volume. And so as we think about how density changes and why density changes, we want to be thinking about both of those things, because that's what's really going to help us understand what's going on in the ocean. So that is a preliminary introduction to temperature and salinity and how they affect density. So I want to think about how changes to the density can cause water to circulate. So we're going to look at a demonstration. If we were doing this live, you would get to do this in person, but unfortunately we can't. So we're going to have this big plastic tank, okay? And then on one side, we're going to pour hot water in. On the other side, we're going to pour cold water in. So in your mind, I want you to be thinking about, okay, so what does that mean about the density on each side? And at the beginning, there's going to be a plastic divider between the two sides that's going to ideally prevent water from either side leaking over. And then we're going to remove the divider quickly and smoothly, and we're going to look at what happens to the water. So there's a couple key things. The first is that the water level at the top is the same. So ideally, you should have a completely flat surface. And we're looking at water that's really hot on this side and water that's really cold on this side. So as with some of the previous slides, I just want you to pause for a second and think about what you think is going to happen when we remove that divider. And then think about why you think that. And again, this is not the kind of thing where there's some sort of bonus points for being right. I just want you to think about, like, what would I expect to happen, and think about your reasoning, and that'll give us something more to think about when we look at the actual demonstration. Okay, so here we go. I wish I could talk to you in person so I could hear your predictions, because I'm sure they're really interesting. So here is the setup. As you can see, we have the hot water on the left, cold water on the right, and we have someone ready to remove the divider. So we're going to watch this a couple times. The first time I'm not going to say anything. I just want you to think about what you're seeing without me talking about it. And then we'll watch it one or two more times so I can talk about a couple things. There we go. Okay, so that was viewing number one. Let's view it one more time. And I just want to say a couple things as we are watching it. So you can see that at the beginning there was already a little bit of water leaking over. It's not a perfectly strict divider. But the first thing I see is that you have this hotter water, which, as I said, is going to be less dense, flowing over here to the right. And then initially, actually, it overshoots the end and starts circulating down and then comes back up. And so by the end of the video here, we've sort of reached not quite equilibrium, but pretty close. You're going to continue to get a little bit of wobbling along this interface. You'll notice that at the ends, we have a little bit of mixing between the two water masses, but in the middle here, we still have a very sharp divide. And so we end up settling pretty much with this two-layer ocean. Basically, we have this two-layer mini ocean with the lighter, hotter water on top and the colder, denser water on the bottom. And so one thing that's interesting to think about is we can see that there's a little bit of mixing towards the ends here. But one thing that's interesting to think about is how long do we think this separation, this two-layer system will persist? Because right now, as I said, it's a pretty sharp divide, except for where we had those collisions with the wall that generated some mixing. And then the other thing to think about is how does this represent the ocean, and how does this relate to processes in the ocean? And we'll talk about that in a minute. But I want to give you some time to think about that first. And if you need more time, you can always just pause the video and think about it, or rewind the video and watch it again if you'd like. So now we're going to do the same thing again, except for this time, instead of having hot and cold water, we're going to have fresh and salty water. And again, just want you to think, especially now using what you just saw with the temperature, I want you to pause and again, think about what you think will happen here. If possible, if you have new evidence now that you didn't have before you saw that first video, or if you have a new understanding, try to incorporate that into your new prediction. And that's something that, of course, we would want to do with students, where as they get new evidence, they want to revise their predictions and think about how to use that evidence to make predictions about a new experiment. Okay, so here is the next experiment. It's actually backwards from the way I drew it on the previous slide, but the dark area is the dark area is the fresh water, sorry, and then the light area is the really salty water. So again, we're going to watch it once, and then we'll replay it and talk about a couple things. You guys did a great job getting two different densities. Holy cow.
It's really salty.
Yes, we went for it. Okay, well, you get the added bonus here of hearing my original commentary from when we first did this. So one thing that's really helpful to know about this is that the lighter colored water here is in fact really salty. They really accomplished a huge density difference between the fresh water and the salt water. So let's just watch it one more time and think about it. So you'll notice again, there was a little bit of bleeding between the two sides. So one thing I think is interesting is on the previous one, we saw how there was some mixing around the ends here where there was a collision with the wall. And you'll notice here that it's actually a lot less pronounced, and maybe that has to do with the more extreme density difference that we were able to accomplish with the salt. It's a lot easier to control how much salt you put in, and then it is the exact temperature you end up with. And you'll notice that here at the end, the divide between the top layer and the bottom layer is even more pronounced. You get a little bit of mixing here, but you can really see that sharp interface between the two things. And you can see like we've paused mid oscillation here. And we've got this pretty nice wave shape. And this is actually what's called an internal wave. So if you look at the top here, you'll notice that there's very little perturbation on the surface. It's pretty flat, but we have this wave motion going back and forth on the inside. And here, since there's nothing external, there's no wind, there's no jiggling, there's nothing else, eventually that'll settle down and damp out. But this is actually a pretty common feature in the ocean, and I'm going to talk a little bit more about why that is in a second. But again, you know, we see this very sharp divide here between these two layers. And so the question is, how does this correlate with what we actually see in the ocean? And how, you know, if this were the ocean, or even if we just had this set up in our classrooms, how long would that divide persist if we didn't do anything else? So let's think about these experiments just in terms of density for a minute. Some of the things I just mentioned are moving on to a slightly different topic. But if you have these two, if we just think about these as two columns of water, one column of light water and one column of dense water, and then there's the same height, so the surfaces are at the same height. Then down here at the bottom, what we have is two columns of water of the same height and different densities, which means that there's different amounts of mass stacked on top. So if you were at a point here on the bottom left, you're going to experience a much lower pressure than if you were at a point here on the bottom right. So what that does is it sets up a pressure gradient from right to left. And so if you're a little water parcel hanging out here in the middle, you've got high pressure over here, high pressure over here and low pressure over here, and that's going to push you to the left. But the only way for the water over here to move to the left is the water, if the water on top moves to the right. And so this process is called gravitational adjustment, but really just means that the water is responding to pressure differences caused by gravity. So typically when we see this in the ocean, in the way we've just seen it in our little lab experiment, it's going to be on a smaller scale than the whole global ocean. You often have what are called fronts in the ocean, where the wind or the wind-driven circulation push two different water masses next to each other, and so you actually end up with a situation that looks remarkably like this, where you force a column of light water and a column of dense water next to each other. And then once you don't have that external force holding the water up anymore, it relaxes and you get this small scale overturning circulation. And the important idea here is that the ocean is always tending towards a gravitationally stable configuration. So we're always moving towards a situation where the lighter water is on top and the denser water is on the bottom. So if you were actually to go out into the ocean, what you would see is these vertical gradients in temperature and salinity and density. And the most important one is this gradient in density. So at the top, we're going to have lighter densities. At the bottom, we're going to have heavier densities. If there's any situation where this doesn't happen, then the ocean will adjust until it does. So for example, let's say you started out with really warm water near the surface, so you had a really low density, and then all of a sudden it got really cold. And so all of a sudden this water at the top, at the very top, is a lot colder than the water right below it. And so that's going to make that water at the very top denser. And so what would happen is that water would sink. The challenge is that you have to consider temperature and salinity simultaneously. So you don't always get this nice monotonic increase in temperature or this nice increase in salinity. Sometimes one is increasing and the other is decreasing, and they just have to compensate for one another so that you end up with a what we call a stably stratified ocean. So again, that just means that we have the light water on top and the heavy water on the bottom. And those differences in density can be because of temperature changes or density or salinity changes. And actually, as we get to the higher pressures away from the surface, those can also be contributed to by pressure. If you've ever been to the bottom of the swimming pool, you feel a lot of pressure in your ears. Just imagine the bottom of the ocean at 4,000, 5,000 meters. It's really high pressure. So even though we say water is mostly incompressible, if you put enough pressure on it, it's not really true anymore. So this is what you would actually see if you go into the ocean. As I said, the ocean will adjust until this is the case. So we saw in that lab experiment what would happen if we had two different water masses next to each other. I just talked about what happens if you have something at the surface. But I just want you to think about what are some other processes that could be happening at the surface, either ones that affect temperature or the ones that affect salinity that might change what's going on in terms of density at the surface. And if you're looking for some fancy new vocabulary, you'll notice that on this plot we have thermocline, and we have halocline and pycnocline. And so in oceanography, we use that suffix cline to refer to this gradient where we have a big change. And so the thermocline is where we see that big change in temperature. The halocline is where we're seeing that big change in salinity. And then the pycnocline is where we're seeing that big change in density. But those are all just fancy words to say big change in temperature, big change in salinity, and big change in density. So we've talked about a bunch of stuff. We've talked about how temperature and salinity contribute to density. We've talked about how if you have two different water masses next to each other and no external forcing, or if we remove the external forcing, that those water masses will adjust until they're in a gravitationally stable situation. And what I want to think about now is if you think back to those temperature and salinity maps, we saw a lot of variation in that sea surface temperature and salinity. And so I want to think about what some of those processes are that are contributing to that. So this is a similar setup to what we just saw. I'm going to pause the video right here before we continue. So it's slightly different because they're not dealing with a two-layer ocean here. We just have water, and then this is a gigantic ice cube. So you could imagine that this is representing an actual chunk of ice, or you could imagine it's representing a process near the sea surface that would make the water around it really cold. So if you think about winter, the atmosphere is really cold, you're not getting a lot of sun. You can also imagine those as stand-ins for this ice. So let's see what happens. They're going to do some really creative use of food coloring to help us see this. So I'm going to pause it here again. So again, all the water in this tank was initially at the same temperature. And you'll notice that in the region around our big ice cube where we added this food dye, now all of a sudden we see this tongue of water, or this tongue of food dye and water descending down into the bottom. So let's continue to watch what happens to that. Once it gets to the bottom, it has to go somewhere. It could come back up, but what you actually see is that it's moving along the bottom of the tank. So if that water is coming down, moving down the side, and then coming across the tank, something has to be moving out of the way and filling in the space where that food dye was. So if we were to watch this for long enough, if the video continued for long enough, you see how you're starting to see this water come up here. What we're seeing here is what's called an overturning cell, or an overturning circulation. And what that means is that you're really getting this three-dimensional circulation where water is moving down from the surface into the bottom and then creating this whole closed circle of circulation. And so what we can think about, this is basically a tiny version of what's happening in the ocean. The ocean is just much more complex. There's multiple basins, and there's not just one ice cube in it. But this is very similar to what's happening in the ocean. And what's really important, and that what I want to emphasize, is that the sea surface is the only place where we can change the properties of the water. Unless we're doing mixing somewhere down here. So, but you know, the sun doesn't reach down here. There's no river inflow at the bottom of the ocean at 4,000 meters. The only processes that are happening down there that might contribute are hydrothermal vents, but in the grand scheme of things, those are really tiny compared to the energy from the sun that we've talked about before. So anything that's happening in the interior of the ocean is just going to happen because of mixing, and we're not going to be able to continue to change the water properties anymore. Okay, so this is one of my favorite graphs. This is what's called a transect from the Atlantic Ocean. So over here on the right, we have the very far North Atlantic, maybe closer into the Arctic. And then down here on the left side, we have just off the coast of Antarctica. You can see Antarctica coming up right here. So in the previous slides, we've talked about how that North Atlantic is really salty, and how it's also really cold. And so what this is showing us is how water from that North Atlantic, which is really salty, this is actually a plot of salinity, it's not density. This is a plot of salinity. You can see this really salty water actually coming down into the interior of the ocean and, you know, penetrating thousands of miles to the south. Oh no. And conversely, you can see this water from the south, which is around the Southern Ocean off the coast of Antarctica, is really actually quite fresh water, also heading into the interior of the ocean. And so what this is evidence of is a really nice illustration of that kind of overturning circulation that we saw in the previous video, where you have something happening here that then descends into the interior of the ocean and then moves south. So this is only salinity, and if you'll notice, this really fresh tongue here is actually above or below this really salty bit here. And so again, we can't think of salinity and temperature in isolation. We have to think of them together. But this is probably one of the best plots that exists for illustrating this overturning circulation in actual data. And this is what you would see basically if you drove from north to south or south to north in the Atlantic on a ship and measured the salinity of the full depth of the ocean every 50 kilometers or something. That's where this plot came from. So to put all of this in context, we can use all these things we've talked about to understanding the three-dimensional circulation of the ocean. So this plot is one that oceanographers love, but there's a lot going on. So I just want to talk about a couple of the things. The first thing is these yellow dots. There's two here in the North Atlantic, and then there's two here off the coast of Antarctica. And those yellow dots represent what we call deep water formation sites. And so those are the only places in the ocean where the water gets dense enough to move from the surface all the way into the deep depths of the ocean. So there are other places where water can sink. If it gets really cold at the surface, as I said, you can have some sinking of that water. And that could happen in theory anywhere, but these are the only places where it can happen on a scale such that the water can sink all the way down. And so those are really important in establishing these three-dimensional circulations, because what happens is as that water sinks, it has to push other water out of the way. Some other water has to rise somewhere in order for the ocean to remain at a reasonable level. And so if we follow these arrows around, you'll notice there's this blue arrow that appears to be on the bottom. And so that's a representation of sort of the deep circulation of the ocean. And so what happens down here in the Southern Ocean, this is where we have the Antarctic circumpolar current, and it's the only current in the ocean that can traverse the entire globe, or all the longitudes without interruption. It's a full depth current, which means you have motion from the surface all the way down to the bottom. And because you have inflows and outflows from all three of the main basins, it's where you get a lot of mixing. So water that came from the North Atlantic is mixed with water that's coming from the South Indian Ocean, water that's coming from the Equatorial Pacific that might have sunk. So this is a huge deal in mixing together water from all over the place. But typically the way we think about this is you'll have water sinking here, traveling south, water sinking here, all of that getting mixed together and then getting shuttled out into the Indian Ocean and out into the Pacific Ocean. And you'll notice that there's no deep water formation sites in the North Pacific. And if you think back to that first plot of density, that's because it's just not dense enough there. It never gets dense enough there to sink to the bottom. So this is called North Atlantic deep water, the water that gets formed up here, and this is called Antarctic bottom water. And so basically those two together, and then this mixing by the Antarctic circumpolar current help set up basically a global version of what we just saw with that ice cube in the tank. So one final thing I want to highlight on this plot is these green regions and these blue regions. And so those kind of correlate with the really fresh regions we saw on the previous plot and the really salty regions on the previous plot. So the North Atlantic, not the super far north, but the North Atlantic has really high evaporation relative to precipitation. So it gets very salty. And then as it moves north, it gets really cold. And so the combination of that very salty and very cold makes that water sink. Down here in the Southern Ocean, the water doesn't start out super salty, but it gets really cold. And then as ice forms, we have this process called brine rejection. And so the ice that forms doesn't contain the salt. And so then you end up with water that's very cold, and the water that gets left behind gets very salty because of that brine rejection. And so that's what helps that water sink all the way to the bottom. And in general, if you think back to those maps of salinity and temperature and density, we can explain all of those processes by a balance between what processes are affecting the salinity. Is it rain? Is it snow? Is it fresh water from lakes? Is it evaporation? You know, if you have water coming or air coming off a really dry area like the Sahara Desert and then moving over the ocean, that water has lots of capacity to take up water, and so that's why you end up with this really high evaporation region. Or we can think about processes that affect temperature, and a lot of that is that shore wave radiation that we talked about previously, but you can also have upwelling where you bring water up from the bottom and so on. So those are all contribute to establishing those patterns of salinity and temperature and ultimately density. So we already talked about this. This is basically just what I said before. So we've looked already at that incoming and outgoing radiation, and we've looked at the zonal heat transports by basin. And so we know that temperature is a factor in setting these deep water formation spots and setting this overturning circulation globally. But we also know that the temperature of the water alone is not enough. And that's one of the things I highlighted between the North Atlantic and the North Pacific. So that's the end of this section about the thermohaline circulation. This is the last time we're going to look at this plot, probably. So I would invite you just to spend as much time as you feel like thinking about the patterns that you've observed and how you might explain them. This might be a good time to ask yourself questions about patterns that you notice that you can't explain in sea surface temperature just by thinking about the incoming and outgoing radiation, because there's really a lot going on in this figure.